So what you see pictured here is an energy diagram. Energy diagrams are always going to be set up the same way. You're going to have the energy, a measurement of the total energy on the Y, and you're going to have the progress of the reaction, which is kind of like the time of the reaction on the X. You're going to have a number of things labeled on this diagram. You're going to start with the products here, the reactants here. So you start with the energy of the products, and usually those lines are going to be horizontal. And you're going to end with the energy of the products over here. You're again then going to see a rising kind of hill. That is going to be the energy of the reactants increasing. Then you're going to see the hill go back down to make the product. So what's actually happening here is the energy right here of the reactants, energy is getting put into the reaction, and the energy that's getting put into the reaction is actually going to break bonds. And then what happens over here is you've gone down the hill, now you're making new bonds to make the products. The name for the energy that is needed from the reactants until when it starts forming new products is called the activation energy. The activation energy is the amount of energy that needs to go into a reaction to have it proceed. Think of it as the activation energy is the energy needed to break all the bonds in the reactants. So you have to climb this big hill, breaking every bond to get to the top. Once you hit the top, this is called the transition state. This is like the momentary state where all the bonds are broken, nothing has reformed yet, and then you go downhill towards the products, and this is where the bonds are reforming. So in terms of energy, the energy is going into the reaction, breaking bonds, breaking bonds, breaking bonds. Then you have a momentary pause where the energy again is zero. There's zero change in energy. And then you go down and energy is being released, bonds are forming, So the activation energy is from the starting point of the reactants up to the top of the hill, the transition state. That is the energy needed to start a reaction. The other thing you can tell from one of these diagrams is whether the reaction is endothermic or exothermic. You see from this reaction that it is endothermic. So in an endothermic reaction, you're going to have the reactants having less energy, Remember, NRG stands for energy. And for exo, you're going to have the products having less energy. So you can tell that just by the height. So you see here, the products are higher in height than the reactants, so this is an endothermic reaction. The other thing you may see with some of these graphs is you may see a catalyst being involved. And remember, a catalyst works by lowering the activation energy, therefore speeding up the reaction. So if you were to draw a catalyst here, all you would do is draw a hump that is smaller. So you're lowering the activation energy, see it's less of a distance, and thereby speeding up a reaction. So a problem you classically would see would be for the graph, label the reactants, the products, the activation energy, and the transition state. Remember, the reactants and products are always going to be horizontal lines because the energy is not quite changing yet. Just by definition, so if we just labeled this with an A and a B, to make it easier to draw on the graph, the reactants are always the starting stuff, so that is always going to be the line, the horizontal line furthest to the left. The products are always the ending stuff, so that is going to be the horizontal line farthest to the right. We could label activation energy as C. Now for this particular graph, you might want to add to it. You might want to draw little horizontal lines going out from where the energy starts, and then an arrow, because what you're showing is C, the activation energy, remember, is the energy needed to start a reaction. It's the energy to get from the starting reactant point up to the transition state. So this whole place right here is the activation energy. And finally, the transition state is letter D, and that's going to be the very tippy top of the hill. And remember, that's the spot where all the bonds have been broken. Another thing you could be asked to do with this is, for example, draw what a catalyst would look like. So I'm going to draw a catalyst in red. So if I did that, I would just draw a line, usually dotted because you're showing it's kind of a new thing. And you're just going to lower the hill height. Notice that the product and the reactant height are still the same. That doesn't change the energy there. You're just lowering the height of the activation energy to show a catalyst.